सवाल सामने आए उससे अंदाज़ा हुआ, I realized that I had not explained it enough. So let me go through that part briefly and then move on from there. The part was about S equal to K log omega. Calm down, please, quiet. नहीं, अभी भी आप लोग खामोश नहीं हुए। एक्साइटमेंट किस चीज़ की है ये? प्लीज़ क्लास शुरू होने के बाद बातें ना करें आपस में। अच्छा, ये सवाल तो अच्छा है आपका बहुत। ख़वातीन
इस वीकेंड तक
हैं?
इस वीकेंड तक
खुशखबरी इस वीकेंड तक नहीं है? अच्छा, ये खुशखबरी होगी भाई, इसी वजह से मैंने कहा।
सर
नेक्स्ट मिड टर्म का टाइम टेबल आएगा। The RO has to give out a timetable of papers, so it is during that break, that period. Quizzes कब होंगे? We haven't decided yet. Weightage कितनी है? Did you go through the first information sheet that I had circulated? You forgot that, so please go through that again. And we may change that also, because we find it very difficult to administer examinations to such a large class. And if you are sitting so close to each other, we would not know if the answer you have written is yours or somebody else's. Because of which taking examination in one hall in an environment like this becomes very difficult. So quizzes will lose meaning if we give you quizzes over here in this hall. And that is why we are rethinking on that issue. Okay? All right. So we were over there, and I had actually taken again. Please, आपस में बातचीत अब ना करें. Okay? Please. I had taken a particular distribution, and that I called NI distribution. And I wrote down the final expression of it, which many of you seem not to have understood. And it sort of was very, obscure for many of you. So I'm going to go through it again, starting with some simpler examples and letting you understand what we are trying to do. Omega. जल्दी जल्दी बैठ जाएं, जल्दी बैठ जाएं। देर से आने का मतलब ये नहीं कि क्लास को आप डिस्टर्ब करते रहे। Omega is the total number of states the system can have. Total number of states, microscopically distinct states that the system can have. And we saw that system can actually have a large number of microscopically distinct states. And I'm going to actually, आप लोग बातें करना ख़त्म करें ना, Please. Total number, that disturbs me. और अगर मैं परेशान हुआ तो फिर मैं आप लोगों से कहूँगा क्लास छोड़ दें, चले जाएं बाहर. Alright? Total number of microscopically distinct states, and I think most of you, or many of you, fail to see how one evaluates total number of microscopically distinct states. And I'm going to take up very simple examples, and from these I will try to tell you how we wrote those expressions that we wrote at that time. So let us say there are 5 objects to be placed in 5 cells or boxes. And if you are going to do this, and the objects are all distinguishable, different balls with different colors, for example, then there are 5 different ways of choosing the ball that was to go into the first cell. So you have cell number 1, 5 different ways to choose the ball that can go into this cell. Number 2, there are 4 balls left, 4 different ways to choose. Number 3, 3 different ways to choose. Number 4, cell number 4 will have 2 different ways to choose the ball, the objects. And number 5 will have only one way. I hope this is very easy to see. Now that means for each of these choices, for cell number 1, 4 choices exist for cell number 2, and for all these choices, 3 choices exist for cell number 3, and then 2 choices for cell number 4, and then only 1 choice. There is no choice for cell number 5, only one way. So there is this total number of ways in which you can choose these balls is equal to 5 into 4 into, which is 5 factorial. So there are 5 factorial different states that you can make out of this whole exercise. You will have 5 factorial number of ways, which is of course equal to 120. Now suppose you do a little different exercise, and you say there are 2 objects out of 10 to be placed in ये परेशान करता रहेगा हैं कैसे लगाऊं इसको to be placed in 5 cells. Now, if you have 2 objects, then there is in the first cell, cell number 1, you will have these many ways of picking objects to put into the first cell. And this happens to be what I wrote as 10 factorial over 2 factorial times 10 minus 2, 8 factorial. let me write it down, write it as 10 minus 2 factorial. There are so many ways of हाँ जरा बुलाइए जरा, ये बहुत गूंज रहा है. हाँ बुला लीजिए. बहुत सेंसिटिव है आज ये. Okay, so there are so many different ways of choosing the 2 objects out of 10 to go into cell number 1. This is the formula. Cell number 2. आवाज बहुत ऊंची है, ये बहुत शो कर रहा है. क्या हुआ? यहाँ से कम हो. कीजिए जरा. क्या होगी? बैटरी डेड होगी. ये हुआ. I will shout. In cell number 2, you are left with 10 minus 2 objects, out of which you have to select 2. And there are so many different ways of doing that selection. That comes out to be 10 minus 2 factorial divided by 2 factorial. Is that okay now? देखते हैं. आप जरा अभी इधर ही रहिए, देख लीजिए जरा आवाज ठीक हो तो फिर जाइए. चले गए वो. अभी बुलाइए भी कहिए, आवाज बहुत ऊंची है, थोड़ी कम करें आवाज. 2 factorial times 10 minus 4 factorial. And I can do this for cell number 3. I will have 10 minus 4 and 2 number of ways, which is 10 minus 4 factorial divided by 2 factorial times 10 minus 6 factorial. And I can continue doing that. ये अच्छा है, आवाज थोड़ी कम कर दीजिए, और कम कर दीजिए, बहुत गूंज रही है आवाज. Now I can continue with that, and for cell number 2 I will have 10 minus 6 and 2, which is 10 minus 6 factorial divided by 2 factorial 10 minus 8 factorial. And for the last one, cell number 1, I will have actually 10 minus 8 and 2, which is 10 minus 8 factorial, which is 2 factorial divided by 2 factorial and 0 factorial. Okay? Now, if I do this, put this all together, so for each of these choices, for each of these many choices, there are so many of these choices, and for each of those combinations, there are so many of these choices, and so on and so forth. And therefore, total number is total number of choices, which is equivalent to saying total number of microscopically distinct states is equal to 10 factorial divided by 2 factorial times 8 factorial multiplied by 8 factorial divided by 2 factorial times 6 factorial multiplied by 6 factorial divided by 2 factorial times 4 factorial multiplied by 4 factorial divided by 2 factorial times 2 factorial and multiplied by 2 factorial divided by 2 factorial times 0 factorial. And this is where these things cancel out. And you are left with 10 factorial divided by 2 factorial times 2 factorial times 2 factorial times 2 factorial times 2 factorial. And you can easily verify that this is equal to 113,400. So 113,400 ways of doing this choice. 13,400 different, microscopically different states. States differing from each other in macroscopic detail on a ball of which color going into which cell. Okay? This is how we can see from very simple examples. And that is what I did for log omega over there.
सर आप ये क्वेश्चन दोबारा एक्सप्लेन करेंगे कि आप उस एक सेल के अंदर 2 बॉल्स बेसिकली आप डालना चाहते हैं?
Right.
2 डालना चाहते हैं?
Right. This is 2 objects. We now want to fix that. We have 10 balls. We have 5 cells, and you want to place 2 balls in each cell, and we have to choose from 10. We have to find number of ways in which we can do that, and that number of ways comes out to be this. Okay, and this is the total number of this is the omega that would go into that expression. Now, if I go back now to my earlier expression, that particular problem. In that particular problem, I said that there is this Ni distribution. That cell number 1 has N1 particles, cell number 2 has N2 particles, cell number 3 has N3 particles. So N1 particles in particles or objects in cell 1, N2 particles in cell 2, etc., for which the number of ways in which you can put them together, being all distinct particles, you will see that this is n factorial over n1 factorial multiplied by n minus n1 factorial over I'm sorry, I should be careful. I will put it in the form of these choice brackets. So combination n and n1, and then n minus n1. Let me write bigger. N n1, n minus n1, n2, n minus n1 minus n2, n3, and so on. When I have that, then I will have eventually omega equal to n factorial over n1 factorial, n2 factorial, n3 factorial, and so on. And then I said log of omega was equal to log of n factorial minus log of n1 factorial minus log of n2 factorial, etc. And when I have this series, I called it log of n factorial minus summation over I log of ni factorial. And then I did the Stirling approximation, used the Stirling approximation. Stirling approximation allowed me to write log of n factorial for large n. It is applicable only in the case of large numbers. Is approximately equal to n log n minus n, and I can write similar expressions for ni, n1, n2, n3, n4, and so on. And eventually I will have log of omega being equal to n log n minus summation over I, and in this summation I will have ni log ni minus ni. Oops, sorry, here something is missing. Okay, here is minus capital N. I'm sorry. So let me rewrite this expression. Minus n, I will say this is approximately equal to minus n, and then minus summation over I, ni log ni minus ni. Approximately log omega is approximately equal to this, out of which, because summation over I and I is equal to capital N, so summation over I and I is equal to capital N. This is plus capital N and minus capital N, so they cancel out, and I am left with log omega being equal to, am I making a mistake somewhere or not being very clear? Is it okay? Log omega being equal to n log n minus summation over I ni log ni. And what I did was that at this stage I said that this expression, this n is sum over I and I. So sum over I ni log capital N minus sum over I ni log ni, from which I can take sum over I ni out, and inside I am left with log capital N minus log ni. All right, and here I did a trick, and I said that I can take an n outside so that inside I have sum over I ni over n, and then inside the bracket I have what did I do? I can मेरे यहाँ पर हाँ all right, I multiplied and divided by capital N, but inside I will have log of ni over capital N. Okay, with a, okay, so what I will do is I will make it capital N over ni, and then identify that ni pi is how you define ni over capital N. If there are n possible ways or n possible states, and the ith state occurs small ni number of times, then the probability of state I is ni over n, when capital N of course goes to infinity, for in this limit of very large numbers. So this log omega is equal to n times sum over I pi log pi. This is what I was doing last time and towards the end of my lecture. Okay? Minus sign, yes, of course, a minus sign. I'm sorry, a minus sign, because that capital N over N, when I reverse that, take an inverse of that, that will fetch a minus sign outside because of this log, and therefore the minus sign. Yes, thank you.
So why did you take small n I to be a large number?
Usually these are very large numbers. Usually number of objects that we have in a gas is of the order of 10 to the power 24, 25, 24. And the number of possible states accessible to the system at a given time is a few numbers, a few states available. 10, 20, 30, maybe 100 states at the most. So the number of particles that are to be found, number of particles to be found in a given state is very large, still very large, about 10 to the power 23.
Do we define states by the position, momenta, or?
We define, the question that he is asking is, how do we identify different states of particles? All right? And the answer is that, and he also answered it. He said, do we identify them with particle positions or momenta or whatever, right? Yes, true. States of particles are, in the classical sense, are identified in terms of coordinates and momenta. This is a result in mechanics, that if you want to identify the state of a particular particle, you identify of a particle or a state of a system. Of a particle, the state is given by coordinates and velocities. Coordinate and velocity, or coordinate and momentum. Okay? And if you have a collection of particles, then coordinates of all the particles and momenta of all the particles will define the state of the system. In quantum mechanics, you have many other quantum variables coming in, and those also will specify the state of the system. Okay? So the state of the system is identified in classical sense by coordinates and momenta of all the particles, in quantum mechanics by quantum numbers, various different quantum numbers. All right. Next point that I want to take up is
So we say that there are only a few possibilities for this system to be found in. Right?
I'm sorry?
There are only a few possibilities or only a few states in which a system can be found. Right?
Okay.
We said that. But position, momenta, they all can be continuous.
Right.
They can take continuous values. They
Right.
don't have to take discrete values.
Right.
So doesn't I have to run from 1 to infinity?
Yes, true. The number of possible states that you have in classical sense. When you have classical sense, then you have actually particles and positions and momentum. Positions would not go from 1 to infinity. Positions specified within the boundaries of the container, where the gas is, where the solid is, or where the system is. And momenta certainly can be from minus infinity to plus infinity, all of them, right? And then we will find out the probability by certain ways of doing the integration over the entire volume. But then the system will say that the system momentum and momenta are subjected to. You see, momenta. If suppose we are taking classical systems, then P square over 2m will specify the kinetic energy of particles. And if there is no potential energy, then energy gets to be specified. So we say that if this is, say, between E and E plus delta E, within a certain range of energy, then your momentum is not going from minus infinity to plus infinity. It is within that region. But if you can take momentum to go from minus infinity to plus infinity if you specify some other particular properties. And you will learn of those things when you get to learn statistical mechanics. All right?
Distinguish between the capital N and omega.
Okay, the question that he's asking is, would you distinguish between capital N and omega? Capital N is number of objects, number of particles that we have taken over here. Number of particles or number of objects. Whereas omega is the total number of distinct macroscopic states that system have, which are microscopically distinct from each other. Okay? Does it answer your question? Okay.
What are the cells in microscopic system?
Could be anything. Could be, different single particle states. Different single particle states. Could be the cells. Or you could specify different regions of space where you want to locate the particles. Okay? But this is very schematic. What I tried to do at that time was trying to connect this relation for S with this relation for S. Okay? And I tried to do this because I just wanted to show that these two, in fact I have already done that in one other exercise earlier. And we were just repeating it over here. And I was just doing this because I wanted to give you a flavor of how this counting goes on in statistical physics. Okay? But we are not going to go into statistical mechanics. Not yet anyway. Okay. Next point that I want to take up is that, as I said, if entropy is defined as minus sum over I pi log pi, and I told you why there should be a minus sign over here. Minus sign is over here because pi, like any probability function, is something between 0 and 1. And for a fraction, entropy, a log is always negative. So because the log of fraction is negative, therefore we have to have a negative sign outside so that entropy is positive. Okay? As we expect it to be. So S is equal to this expression actually tells you that this is summation over I log pi average. Because if you want to find average of any particular quantity, just a second. If you want to take average of a particular quantity, say xi, then xi average is summation over I xi times pi. Okay? This is how you define averages. You multiply each quantity with its probability and sum over all of them. That will give you x average. Your question? Sorry? Ah, you are right. You are right. You are right. Okay. n नहीं, n जो है वो मैंने right. मगर हमारी जो ओरिजिनल डेफिनेशन है ना वो ये है. n के साथ वहाँ पे that was a something which will be absorbed somewhere, but here in this particular case this is how we define entropy. Okay, so k is absolutely necessary, minus k, otherwise the units will not be the same. Correct. So this is k goes here, and this is average of log p in this sense. So entropy therefore is an averaged quantity. And there are other average quantities also. I'm sorry? Okay, you are right. एक और मेरी गलती पकड़ी गई. जब आप एवरेज लिखेंगे तो समेशन नहीं लिखेंगे यहाँ पे. ओह, इतनी गलतियां कर रहा हूँ मैं आज. करेक्ट. और फिर आप लोगों की गलतियां खूब पकड़ लेते हैं. So xi average is given by this, and therefore this particular expression would be like taking the average of log pi. All right, good. इससे मालूम तो होता है कि आप लोग देख रहे हैं गौर से चीज़ों को. गुड. एक और चीज़ भी है जो कि एवरेज्ड आउट क्वांटिटी है. एक्चुअली थर्मोडायनामिक्स के सारे वेरिएबल्स एवरेज्ड आउट वेरिएबल्स है, एवरेज क्वांटिटीज़ है सारी की सारी. और दूसरी क्वांटिटी जो एवरेज क्वांटिटी है वो U है. U को मैंने इस वक्त यहाँ पे कैपिटल U की फॉर्म में लिखा. आई मे नॉट क्वाइट एडहियर टू दिस कैपिटल. इंटरनल एनर्जी. Internal energy happens to be the average of all single particle energies. All energies, and therefore this I can write this as summation over I epsilon I pi. This is an average over all, average of all energies. What is internal energy? Therefore, internal energy is sum total of all the energies that can exist in the system, in the various degrees of freedom of the system. So, sum total of all the energies associated with degrees of freedom. And degrees of freedom are not just, positions and momenta. There are many, many more. There can be, you have kinetic energy, you have potential energy. Potential energy in the sense that potential energy of interaction. You can have, for example, if you have a diatomic molecule of this kind, where two atoms are together, then you have two additional degrees of freedom available to this molecule. One is the vibrational, when the two atoms vibrate against each other, and therefore there is a vibrational energy. And then they can also rotate about an axis perpendicular to the line joining them, and this rotation also has certain well-defined states. So rotational energy. Rotation is again another degree of freedom. If the atoms have certain magnetic moment over them, then that magnetic moment can be another source of absorbing energy. So internal energy is all those modes in which any energy coming in from outside can be absorbed into the system. Or when the system is giving out its energy to the surroundings, then all the modes can give up their stored energy. So this is all the stored energy, rotational energy, magnetic energy. I'm not specifying what that energy is. And electrical energy. Elastic energy is one common thing that we often see around ourselves. So all of these, sum total of all of them is the internal energy of the system. And internal energy therefore is an average quantity like this. And if suppose temperature, if temperature is defined for the system, is described for the system, if it is known at what temperature the system is, then the probability Pi in such a situation, which I have written as system for which temperature is defined, this probability is equal to exponential of minus epsilon I over kT divided by summation over j exponential of you would like me to write this j j exponential of minus epsilon j over kT is the probability. I think I explained this in the last lecture, right? And therefore u would be equal to summation over I epsilon I exponential of minus epsilon I over kT divided by, I can take this divided by over here, summation over j exponential of minus epsilon j over kT. And I hope none of you ever makes this mistake of crossing out exponentials and whatever you can cross out. I hope you don't make that mistake, because this is a summation in the numerator and a summation in the denominator. Okay? So this is a plus b plus c plus d. You can't cross out terms. Okay? So with this then, you can actually calculate internal energy in this manner. All right. So we are now slowly moving to, we have defined entropy, we have seen the microscopic origin of the entropy function, we have seen what internal energy is all about, microscopic origin of the internal energy. We will have to go back and to the first law, the way we wrote first law, dq plus dw, heat and energy. Let me, consistent with my notations earlier, I wrote capital Q and capital W. Okay? For W, we wrote dW, we wrote minus P times dV. When we said, when we wrote this, we actually had in mind mechanical systems, because you were running engines. You were worried about the way engines would run. And engines would run by changing volume and under pressure. But there can be other kinds of work also. I can write down a few. dW equal to mu times dN is called chemical work. Chemical work. By changing the number of particles in the system, you change the chemical potential. Or chemical energy is chemical potential multiplied by the change in the number of particles. I can write dW as H times dm, where m is magnetization and this funny looking H is magnetic field. So magnetic field multiplied by change in magnetization is what is called magnetic work. All right. I have to spare the usual form of H for a different variable, so I put this H in this funny looking shape. I can also write dW as tension, I will write tension as tau times dl. Elastic work is when you have lengthening of something under tension. Okay? And this is equal to, can also be stress multiplied by strains. Some external stresses introduce strains into the system. And epsilon over there is being used for, let me use a different kind of epsilon over here to often, this is the usual notation for elastic energies. There is a change in strain of the system as a result of applying certain stresses, and the total amount of energy is equal to what you call the elastic energy. This also, I could write dW as change in polarization, and for polarization I will have to write a different P, when you introduce an electric field into a dielectric medium. So you subject a dielectric medium to electric field and polarization appears, and that is what you call electric work. So you actually then, work can be of various different kinds. Not just mechanical work, which is over here, and I will actually now start to put under this the subscript mechanical to show that this is only one kind of work, mechanical work. Then there are other kinds of work that are legitimately works, and whenever we want to include them in our discussion on thermodynamics, we should know how to include them. Now, with this, we will reformulate the first plus second laws of thermodynamics. We are putting now the first and second laws of thermodynamics together. And that is done by saying that du is equal to TdS minus PdV. And this is going to be the center point of the rest of our discussions of thermodynamics. Here we have already replaced dq by TdS and already replaced dW by minus PdV. And I could take an enlarged view this is for mechanical systems, but also at times you say for fluid systems. Fluid systems means gases and liquids in which pressure and volume are significant variables. And those are the fluid systems. कौन सा T?
Temperature.
This T is temperature. Okay? We said that ds, change in entropy, is equal to dq over T. So dq has been replaced by this. Okay? For fluid systems, and therefore for fluid systems I can write du as T times ds minus P times dV plus mu times dN. This is an addition to the usual first law of thermodynamics, where then we consider actually open system. Open system. As if we open the window over here and allow this environment in this room to exchange particle also. Air can go out and come in. All right? Particles can go out and come in, depending upon the difference of chemical potential between this room and the outside room. So, chemical potential drives change in the number of particles, number of moles, number of particles. Pressure difference drives change in volume. All right? And this is thermal energy. So here we have a statement which describes energy systems that play together in a system. जिसमें केमिकल पोटेंशियल की जिसमें नंबर ऑफ पार्टिकल्स वेरी कर सकते हैं. सिस्टम इज ओपन. तो वो इंटरनल केमिकल पोटेंशियल को नहीं रख सकते. ऑलराइट. योर क्वेश्चन वाज जिसमें केमिकल पोटेंशियल वेरी करेगी. केमिकल पोटेंशियल विल डिटरमिन whether the system should exchange particles with surrounding or not. Okay? Yes, chemical potential will also vary. We allow that also. But the thing is, the system is now open and can exchange material with surroundings. Okay? So this will be the internal energy. This is thermal energy. This is mechanical energy. And this is chemical energy. Okay? And if in the place of this I could include any of these other things, I would have those energies also. Work has the same dimensions as energy. We have come to understand that, right? Work, heat, and energy. So work and heat have the same dimensions as energy, and therefore in this case, in all these cases, this combination has dimensions of energy. When you have polarization multiplied by electric field, then you define polarization in such a manner that when you multiply polarization with energy, you will get dimensions of energy. When you multiply that with electric field, you will get dimension of energy. Similarly, this is defined in such a manner, as strains are defined in such a manner that when you multiply strains with stresses, you will get the dimensions of energy, and so on and so forth. Okay? So here we have, therefore, an enlarged definition of the first and second laws of thermodynamics put together. Right? All our understanding in the last, how many lectures? 10 lectures so far? Yeah? Yeah. In the last 10 lectures have all been towards trying to get an expression of this kind. This is going to be now the basic equation with which we will start any discussion on thermodynamics from now on. Or wherever you are. You will not go back to Carnot engine and start discussing things from there. You will start discussing things from a basic principle of conservation of energy, which is what this statement is. Basic principle of conservation of energy. Okay. Such an expression, I will for the moment I will leave out this question of open systems, and I will work with this formulation. It is easier to do. Not that we cannot include, we can start from here, but this is at times, if suppose systems are not open systems, are connected. Let me also make this statement here. Perhaps you have already understood, but still let me repeat this. A system which is connected to a heat reservoir with which it can exchange heat on account of some temperature difference and has mechanical energy is given by this equation. It is connected to a heat reservoir. This system will be connected to two kinds of reservoirs or a reservoir which is both a heat reservoir as well as a matter reservoir. It can supply matter as well as it can supply heat. It can do both. So this is what we mean by an open system. Let us remain confined to this and let us start looking at some elementary things out of this. The statement that I am going to make is about this algebra of okay, let me do it here anyway. This is about a little bit about algebra of partial differentiation. Okay, variations in parameters. There are so many parameters floating around. If you are taking changes in some parameters, then those changes are governed by the algebra of partial differentiation. So don't get scared. I will put them in the simplest possible form. You will find it very easy to follow. Those of you who are not trained in mathematics. Okay. The point is that if there is a function f, which is a function of x and y, then a change in f is given by partial differentiation of f with respect to x when you keep y constant times dx plus partial differential of f with respect to y when you keep x constant times dy. I hope this expression is familiar to all of you. Right? Right? Anybody here who had not seen this before? No, all of you had seen it before. Okay? And these partial differential expressions follow a certain way. And I'm going to write down those formulae once and for all so that you can follow them wherever. Suppose you have number one, f being a perfect differential. This was the accusation against Q and W from the beginning, when everybody said that Q and W are not perfect differentials and therefore you put a slash on D to distinguish them from other variables. For f, if f is a perfect differential, then what you have is that d by dy of df by dx at constant y, and you do this partial differentiation with respect to x, is the same as partial differentiation of x with respect to x of df by dy at constant x when you do this at constant y. Okay? This is how you express the property of a function being a perfect differential. Or, in other words, I could say that if I could write this as a times dx and b times dy, then what I am saying over here is, therefore, d by dy, dA by dy at constant x is the same as dB by dx at constant y. Okay, I have called this expression x, A, and this expression B. and wrote it in this form, and then this thing is how I can write over here. Okay? Some more things. Because we have so many variables running, so let me get to suppose f is a function of not 2 but 3 variables, x, y, and z. There are so many variables in thermodynamics floating around that you need to take more than 2. F, x, y, and z. So by definition, as I said over there, by extension, it is partial differential of f with respect to when you keep y and z constant times dx, plus partial differential of f with respect to y when you keep x and z constant times dy, plus partial differential of f with respect to z when x and y are kept constant times dz. All right? This is a simple extension of that expression that I wrote over there. And one other property of partial differentiation is that dx by dy, if I take inverse of this, suppose it is at constant z, and I take an inverse of this quantity, this will be equal to partial differential of y with respect to x when I keep z constant. Okay, I can easily invert this. Okay. Also, I can write partial differential of x with respect to y at constant z as equal to, I can insert some other variable in between. Partial differential of x with respect to, say, some variable t at constant z divided by partial differential of y with respect to t at constant z. I can do that too. That is also allowed. Okay? That is also allowed. And there is one famous identity that floats around, which is that partial differential of x with respect to y at constant z multiplied by partial differential of y with respect to x at constant z multiplied by partial differential of z with respect to x at constant y. Oops, sorry. Here I have to have x. I'm sorry. This is all messed up. Y with respect to z at constant x and x at constant y. Okay. This is kind of a going in cycle. X, y, z, y, z, x, z, x, y. This is equal to -1. Okay, this is another identity that is very helpful. And I would like you to please note them down, because in the next few lectures, these are going to be using them for various manipulations. Would be one of the most common things we'll be doing in the next few lectures. So note them down. A result of this is this same thing I could write as partial differential of x with respect to y at constant z is equal to minus partial differential of z with respect to y at constant x divided by partial differential of z with respect to x for constant y. You can easily see it from here, from this and this expression. You can see these from these two expressions. Okay. These are the important relations that we would encounter in our discussions. So let me go back now to describing some important relations. Let me go back now to the expression du equal to TdS minus PdV. This expression tells us that changes in U are brought about by changes in entropy and volume. ds, du is brought about by ds and dv. So changes in U are brought about by changes in S and V. Which means I can write U as a function of S and V. Alright? Because as this law tells you that U must be a function of S and V. If this is so, then du is equal to partial differential of U with respect to S when you keep V constant times ds plus partial differential of U with respect to V when you keep S constant times dV. Alright, I've used that kind of relationship over here. Alright? And the conclusion is, the conclusion is that temperature, if I can compare this with this, temperature is equal to du by ds at constant V, and pressure is equal to minus du by dV at constant S. This is very interesting. You see, there are certain quantities which are thermodynamic variables. Are like temperature, volume, pressure, internal energy, entropy, and maybe chemical potential and number of particles. These are thermodynamic variables, right? Some of them are extensive variables. Extensive in the sense that if you take a system and you divide the system into two equal parts, then that quantity also gets divided into two equal parts. So for example, energy, volume will get divided into two equal parts. If a system has volume V, if I divide it into two equal parts, volume will also get divided into two equal parts. Similarly, if system has total energy U, if I divide it into two equal parts, energy will also get divided into two equal parts. Those will be extensive variables. So V and U and S and N are extensive variables. There are other variables also which do not get divided. If you have a box at temperature T and you divide into two equal parts, temperature of each part will be the same as the original temperature. Similarly, pressure will be the same as the original pressure. So those will be called intensive variables. And intensive variables are temperature, pressure, and chemical potential. Okay? What we are showing over here is that intensive parameters, intensive variables, are differentials of extensive variables. Intensive variables are differentials of extensive variables. We just see this over here. Okay? This is what comes out. In fact, I can also add, if I had an open system mu dn, and if I had over here a function of n, and therefore an additional term over here plus du by dn at constant whatever, now this time it will be v and s, times dn, then I could easily see that mu is equal to partial differential of energy with respect to n at constant s and v. Okay? Is that clear? Yeah.
Can you clarify the difference between intensive and extensive variable?
If you divide the system into two equal parts, extensive variables will get divided, intensive variables will not get divided. Okay? This is the simplest definition. Okay? Mu, therefore, is again a derivative among extensive variables. This is an intensive variable given as a differential of extensive variables. All right? So you have, therefore, these relations, and it turns out that you can actually, if a system can be described by a relation among all its extensive variables, then intensive variables can always be obtained from that equation. Okay? Let me rewrite this statement. Let me write down this statement. If there exists a relation among extensive variables, then all intensive variables can be derived from it. Derived from such a relationship. Okay? And this relation that I am talking about is called the fundamental equation. It is called the fundamental equation because once you know this kind of relationship, then you can actually write down the intensive parameters from this, and therefore once you know intensive parameters, then you can easily obtain from this the equation of state. Alright, this is the last point that I wanted to make over here. The next time we will do two things. Number one, we will take a fundamental equation that somebody says is the fundamental equation, and from it we will work out all the intensive parameters and the equation of state. And secondly, we will look into what different energy functions exist in thermodynamic systems.